On this worksheet, we're going to solve a few different types of problems that involve either a weak acid or a weak base and require us to use the equilibrium constants, Ka or Kb. The first problem is asking us to calculate the pH of a 5.6 molar carbonic acid solution. Carbonic acid is a weak acid, and the reason that I know it's a weak acid is because a Ka value has been provided. Whenever you're being provided with a Ka value, you know for sure that it's a weak acid because strong acids do not have Ka values. In order to calculate the pH, we need to know the H3O plus concentration because the pH, as you know, is equal to the negative log of the H3O plus concentration. So we have to figure out how much H3O plus is going to be produced by a 5.6 molar carbonic acid solution. And the way that we go about doing that is by making an ice table. H2CO3, our acid, reacting with water. This is going to be an equilibrium reaction because it's a weak acid. The products of this reaction are HCO3 minus and H3O plus. How am I able to predict the products of this reaction? Well, I know that H2CO3 is an acid. I know that because there is a Ka value, A meaning that it's an acid. Because it's an acid, that means it is a proton or an H plus donor. So I know that when it reacts, it is going to lose one of its hydrogen atoms. It's going to go from 2 hydrogens to 1, and the charge is going to go down by a +1. So from neutral, it's going to go down to a -1. With this balanced equation, I'm going to make an ice table. The initial concentration of our carbonic acid is 5.6 molar, and initially, before anything happens, we don't have any products at all. I'm not going to be filling anything in underneath water. Water in this equation is a pure liquid, and therefore it isn't going to be included in any of our equilibrium calculations. I'm not adding just to save space that the other 3 substances on here, they are all aqueous. So again, what we need to be able to figure out in order to solve this problem is the H3O plus concentration once the solution reaches equilibrium, and that's going to be represented down here at this particular box. So this is what we're trying to figure out. So we know that some of the H2CO3 is going to react. We don't know how much of it's going to react because this is an equilibrium equation, but we know that some will react. We also know that we're going to be producing some HCO3 minus and some H3O plus. Because the stoichiometry in this equation is 1 to 1 to 1, however much X we're reacting, that's how much X we're making over here on the product side. When this reaction gets to equilibrium, we're going to have 5.6 minus X of our H2CO3, and we're going to have X HCO3 minus and also X H3O plus. So all we have to do is figure out what X is, and we'll be able to plug that in and calculate pH. Now, because the Ka value is so small, 10 to the -7 is an extremely small number, we are going to make the assumption, just based on the value of Ka, that this reaction really doesn't proceed very far to the right, meaning that most of the substances in this system are just the reactants. Very small amount of this actually reacts. This means that the value of X is tiny. The amount that is actually reacting is extremely small. And compared to 5.6, the value of X is really, really small. We're going to make the assumption that the value of X is so small relative to 5.6 that when we actually do this subtraction, 5.6 minus X, it's going to round itself up to 5.6. How could that maybe even be possible? Like, if this is really confusing to you, what if the value of X was something like this small right here, and we did the math on that and subtracted that and then rounded it back to just 2 sig figs? It's going to round itself back to 5.6. So that's exactly what we're assuming here. We're assuming that X is a tiny number compared to 5.6, and that after the subtraction is done, it's just still going to be 5.6. That's going to make the solving for the value of X, it's going to make it way easier. So to solve for the value of X, we want to set up an equilibrium expression. The equilibrium expression is going to be our products, HCO3 minus times our other product, H3O plus, and divide that by our reactant H2CO3. Remember, we're leaving out the water because it's a pure liquid. Liquids don't show up in the equilibrium expressions. The value of Ka is 4.5 times 10 to the -7. I'm taking that from up here. Our term for HCO3 minus is X. That's coming off the ice table. Our term for H3O plus is X, also coming off the ice table. And H2CO3 is 5.6. So now we're just going to do some algebra. 4.5 times 10 to the minus 7 times 5.6. And then I'm going to take the square root of that number to give me the value of x. X is 0.00159. Remember I said that x, we were going to assume x was really, really small. If we do 5.6 minus 0.00159 and then round it back to two significant figures, it just ends up being 5.6. You can check that on your calculator if you'd like. The value of x is the H3O plus concentration. And so now we are ready to calculate the pH. pH is going to be the negative log of the H3O plus concentration, which is 0.00159. And that is a pH of 2.799, 2.8. So there's a lot of steps involved. None of them are that hard. You just need to remember to, not skip any steps and go through the whole entire process. So we have down here a pretty similar type of problem. This one is asking us something a little bit different. So it's giving us, again, a weak acid. We know it's an acid because we're given a Ka, not a Kb. And it tells us that the pH of that solution is 2.55. We're being asked to figure out what the Ka value is. So regardless of what these problems are asking you to do, whether it's asking you to calculate Ka or whether it's asking you to calculate pH or, anything like that, you should always start by writing the balanced equation and setting up an ice table, because you're always going to be using ice tables to solve these problems. So since we know that it is an acid, we're going to be taking away an H plus from our original molecule. That makes C5H9O2 minus, and our other product is H3O plus. And then let's get ourselves ready for an ice table here. We know that the initial concentration is 0.55, and initially we're going to have no product at all, and then we're going to react some of this HC5H9O2, and at equilibrium we're going to have 0.55 minus X, and X, and X. So this problem is a little different in terms of what we're being asked to come up with. We're being asked to solve for Ka. It tells us that the pH of the solution is 2.55. So pH is 2.55. And that means, since we know the pH, we actually have the ability to calculate H3O plus. To get H3O plus, all we have to do is take the anti-log of the pH, 10 to the negative pH. So our H3O plus concentration for this is 10 to the negative 2.55. That is our value of H3O plus at equilibrium. So in this situation, we actually know what the value of X is. We don't need to use that symbol X in our ice table. We know that X is 10 to the negative 2.55. And that's the value of X, just period. Like, that's the value of X for all of these spots right here. 10 to the negative 2.55, 10 to the negative 2.55, and 10 to the negative 2.55. And then also down here, 10 to the negative 2.55. We can probably make the assumption that this is really small compared to the 0.55, and that we can just, take it out of the equation completely, but I'll leave it. Now remember, we're being asked to calculate the value of Ka. So we want to set up our equilibrium expression, C5H9O2 minus times H3O plus over our reactant HC5H9O2. Remember, we leave out water because it's a pure liquid. And then let's plug in what we have. 10 to the negative 2.55, that's our value of C5H9O2 minus. 10 to the negative 2.55 is our value of H3O plus. And 0.55 minus 10 to the negative 2.55, that is our value for HC5H9O2. So now we just need to figure all of this math out. So I'm putting 10 to the negative 2.55 into my calculator, and then I'm going to square that, and then I am going to divide it by 0.55 minus 10 to the negative 2.55. And I got an answer of 1.45 times 10 to the negative 5. That is our Ka value. We've got, I believe, one more to go. Yes, one last problem to go. This one is asking us to calculate the pH of a solution that is a base. I know it's a base because we have a Kb instead of a Ka. So this one is going to be pretty similar to the first problem that we did. Now, always with these, no matter what type of, whether it's an acid or a base, no matter what it's asking you to do, like I had said, first thing you should always do is write an equation and set up an ice table. This is a base, not an acid, which means it's not an H plus donor, it's an H plus acceptor. So that means that we want to increase the number of hydrogen atoms by 1. So instead of NH2, it's NH3, specifically it's NH3 plus. And that means that water is our acid. So instead of H2O, we have OH minus because water is losing the H plus. From here, we're going to make our ice table. The initial concentration of C3H2NH2 is 1.25 molar. Initially, we have no reactants or no products. We are, I don't know how that became a 5. We are going to lose some amount of our reactant and make some amount of our products. And at equilibrium, we will have 1.25 minus X of our reactant. We will have X of each one of our products. We are going to write an equilibrium expression. This equilibrium expression is a Kb. Still set up the same way though, products over reactants. CH3, CH2, NH3 plus times OH minus over CH3, CH2, NH2. We're going to plug in, actually let me put in the value of Kb first, 6.46 times 10 to the minus 4. And that is going to be equal to our two products, which are each represented by X, and our reactant, 1.25 minus X. Oh, but remember, we're going to make the assumption that X is really small, so this is just going to be 1.25. 1.25. We're always going to be making this assumption with our acid-base equilibrium problems because the Ka and Kb values are so small, and this makes the problem so much easier to solve. So we are going to take this equation right here, and we're going to solve for X. 6.46 times 10 to the minus 4, multiply that by 1.25, and then take the square root, and that gives us an X value of 0.0284, and that is our OH minus concentration. So that is the molarity of the OH minus. Our goal here is to calculate the pH of the solution. What we can do with this number is calculate the pOH. The pOH is the negative log of the OH concentration. So the pOH is going to be the negative log of 0.0284. And then once we know the pOH, it is 1.55. From there, we can calculate the pH using our equation pH plus pOH equals 14. So 14 minus the 1.55 is 12.45.